This lecture is on Chapter 7. This is on reactions in aqueous solution, although it talks about sort of general reaction chemistry as well. The first part here is to identify or understand what's the difference between an electrolyte and a non-electrolyte. Electrolytes are those substances that will dissolve in water and produce solutions of ions as a result. And non-electrolytes are ones that will dissolve in water but do not produce ions in solution. And as you can see here, electrolytes, because they separate into ions in solution, they can conduct electricity. On the left, a solution of sodium chloride. A solution of sucrose, while it can dissolve in water and form an aqueous solution, does not dissociate into ions, and so it does not conduct electric current. We will further identify electrolytes into strong and weak categories. Strong electrolytes are those that dissociate to a large extent into ions when dissolved in water. Essentially, we consider this reaction to completion, that if you have hydrochloric acid, that it will mostly dissolve into its ions, H plus and Cl minus. Weak electrolytes are those that dissociate just to a small extent into their ions when dissolved in water. And the way that we represent that is that double-sided arrow. It shows that there's an equilibrium that exists between the forward and reverse reactions here. So both the complete electrolyte stays intact, as well as part of it dissociating into its ions. This is a table from your text that you should be familiar with, I think. Yes, it's on page 238. You should know not only the difference between strong and weak electrolytes and non-electrolytes, but be able to identify the ones that you see here as to which they are. And there's some further categories that can help you do that. The first is that strong acids are also strong electrolytes. So you should know what the strong acids are, and also that they are strong electrolytes. And the ones that you need to know are the ones that are listed here. Also, ionic compounds are typically strong electrolytes. You can see several that are listed here. Weak acids, and there's just a couple listed here that you should know, are weak electrolytes. And then molecular compounds typically are non-electrolytes, like sucrose as the example before. Most compounds that are organic in nature are non-electrolytes. So methanol, ethanol, you also see listed here, would be considered non-electrolytes. The type of way that we show the dissociation in water is what you see here. So these are just two examples of dissociation equations. And what you'll notice is that the ions are shown, how they essentially split apart there. A couple of things about this: when you have a compound that has a polyatomic ion, that polyatomic ion stays intact when it dissociates. So you'll notice here in the sodium sulfate example, the first example, that dissociates into sodium and sulfate ions. And that is always the case. So when you have a compound that has a polyatomic ion in it, when it dissociates, that polyatomic ion stays the same. Also notice the charges here, and for polyatomic ions you would use your chart to know what the charge on sulfate is. So the charge on sulfate is always -2. And for other compounds you would use their group number, unless you have other information. So sodium's in group 1 would have a +1 charge. The next example, iron bromide. The bromine is a halogen, so it's got a -1 charge, and to balance that off in that compound, the iron must have a +3 charge. We'll talk a little bit more about that in a bit. Other types of reactions and other ways that chemical reactions can occur. Several of these we'll talk about further on, but here's just the class of different types of reactions, the general ones. A precipitation reaction is one where you have aqueous solutions and they're reacting together, and one of your products is a solid, and so it precipitates out of that reaction. So as it says, processes in which soluble ionic reactants, so these are aqueous solutions, yield an insoluble solid product that falls out of solution. And we'll talk a little bit about how you predict those in a bit. Another class of reactions is acid-base neutralization reactions. What we see here is an acid reacting with a base to yield water plus a salt. It is not always, as is shown here, sodium chloride. but a salt is the combination of the ions that are left after you remove the water. One thing to note here is if you see that you've got hydrochloric acid and sodium hydroxide, the water comes from the hydrogen from the acid and the OH from the sodium hydroxide. And so you'll see what's left is the ions NaCl. And so that's how you can predict the product, the salt product that you'll get. Another class of reactions are redox reactions. These are one where electrons are transferred, and we'll talk more about those in a little bit. Okay, when we're looking at aqueous reactions and ionic equations, there are several types of equations we use to show these reactions. The first is a molecular equation, and you should be able to write all the three that I'm going to talk about. The molecular equation shows all the substances that are involved in the reaction, and they're written with their complete formulas as if they were molecules. So notice here you do not see any separated ions, and that's because this is a molecular equation. So when you're asked for a molecular equation, this is the format that you'll write, and so everything is written intact altogether as if they were molecules. What I'll show you next is how we write other types of equations here to show how they do dissociate into their ions. And notice also we do have a precipitate here, and the solid tells you that it's a precipitate. So when you look at the phases, that's one way to identify that this is precipitation. The second type of equation to be able to write is an ionic equation, and this is one where you show all the strong electrolytes written as ions. So again, that goes back to looking at the table of what is a strong electrolyte, what is a weak electrolyte. You'll need to know that in order to be able to write these ionic equations. So your strong electrolytes are written as ions. Again, they're separated out. So if we look at that lead nitrate, for example, to start, we know nitrate is a polyatomic ion. It has a charge of -1. And the lead then must have a charge, and since there are two of them in that compound, the total charge on nitrate there is -2. So that means that lead in that compound must have a charge of +2. This is really important. You need to be able to identify what the charges are on different substances, and it's not often, for the case with your transition metals and those in the middle of the periodic table, you can't necessarily use group number to predict their charge. So you have to use the actual compound itself to predict the charge. And again, that's by using the fact that we know that nitrate is -1, and there are two of them shown in that lead nitrate compound. So the total charge on nitrate is -2. So that means the charge on lead in that compound must be +2, because remember there's no overall charge here on the compound. So that's how we determine the charges that you see. And then in terms of the numbers that you see, that's just reflected by the, essentially both the subscripts and coefficients are used as coefficients in your equation. So for example, the lead nitrate splits into lead and nitrate ions, and you have two nitrate ions. You can see that in the formula, and so that's why the 2 is written in front. And potassium iodide splits into potassium and iodine ions. Those or +1 and -1. Potassium's in group 1, iodine's a halogen, so it's in group 7, so it has -1. And because there's two of those to that compound, we know that we have 2 of each of those types of ions. So that's where those came from. And then the right-hand side of the equation, any solid that you have stays intact. So the lead iodide solid precipitate is written just as is because it's not dissociated in any way. The ions that we have, potassium and nitrate, are written. That's from the potassium nitrate that's in aqueous solution. Again, it'd be able to split that up. The potassium nitrate is a polyatomic, so it stays together. Nitrate has a -1 charge, so potassium must have a +1 charge. And there's two potassium nitrates in your formula, so you have to put a 2 in front of each of those ions. The next we're doing here, so this is the full ionic equation that you see here. The next type, or the third type of equation to be able to write, is what's called a net ionic equation. In order to do that, you have to understand what this next part is, and that is to identify spectator ions. So these are ions that essentially do not undergo any change, and the way we see that is that they appear on both sides of the reaction. So if you see any ion that appears on the left and the right side of the equation, then those are spectator ions and are not written in the net reaction. So you can see they're all in boxes there. And so we get to the net reaction, which are the ones that are left. So the lead ion and iodine ion coming together to form that lead iodide solid product. So again, just to go back here, you can see that removing all those spectator ions that appear on the left and the right, you can see the three things that are left. There should be a box around that 2 in front of the nitrate ion. I'm not sure. Just an error there. Okay, so you should be able to write molecular, ionic, and net ionic equations for these types of reactions. The next thing to be able to do is to identify in these reactions if there's something that is precipitating out, meaning it's forming a solid. And there are solubility guidelines that you should know in order to be able to predict this. Solubility tells whether something will dissolve in a given amount of solvent. So here are the guidelines to follow, and they're also written on page 241 in your text. So it's kind of like a little puzzle. You can you look at your your compound and then you see what it fits to either of these two. So number 1, a compound is soluble if it contains one of the following cations. So if you have any of the cations that are listed there, then your compound is soluble. A compound is soluble if it contains one of the following anions. So if your compound contains anions that you see there, then it's considered soluble. The exceptions that you see, I'll just talk through that. So it says a compound is soluble if it contains one of the following anions. You see halide, chlorine, bromine, iodine. And under that, except silver +1, mercury +2, and lead +2 halides. So that means that if you have the silver, mercury, or lead halides, they would not be soluble, and so that means that they would precipitate. Okay, so you have to kind of piece these things together. If something is soluble, it means it stays in aqueous solution. If it's not soluble, that means it's going to fall out of solution and precipitate out. So you can see the example, the next one, nitrate, perchlorate, acetate, sulfate, except those 4 sulfates, strontium, barium, mercury, and lead sulfates. So those would precipitate out. The strontium, barium, mercury, and lead sulfates would precipitate out and form solid products. The other thing to note, just going back to number 1, it says a compound is soluble if it contains one of the following cations. If you have a cation that's not listed there and it doesn't follow anything under the rule 2, then you would say that that's insoluble as well. Okay, so you have to look carefully at all of the rules to figure out if it meets any of the solubility requirements. If it doesn't, or if it falls into one of those exception categories, then you have something that will be precipitating out. So here's an example of using those guidelines. So we want to write the molecular, ionic, and net ionic equations for the reaction that occurs when aqueous solutions of silver nitrate and sodium carbonate are mixed. So the first thing is the molecular equation. So we write the chemical formulas of the products. We use the rules there, so I'll talk through that. This is essentially, all of these are double replacement reactions. So if you think about the first reactant being AB, the second reactant being CD, then you're just recombining the 2 products there to form CB and AD as listed. So silver nitrate and sodium carbonate, the silver positive the cation will recombine with the carbonate anion to form silver carbonate. And then the sodium cation of the second compound will combine with the nitrate anion to form sodium nitrate. Okay, so they're essentially sort of swapping partners there. And the other thing to keep in mind are your charges in order to write the formulas correctly. So that's the other piece to this. So in the first one, AgNO3, if you look up NO3 on your polyatomic ions chart, you'll notice that I think it has a charge of -1. I should have the chart in front of me. So you know silver has a charge of +1 in that compound. So when you go to write silver carbonate, and you find out that carbonate's charge is -2, that means that you're going to need 2 silver ions for every carbonate ion. So that's where in the product you have that Ag2CO3. That's to make sure that you're balancing out those charges. If we look back at sodium carbonate, carbonate has a charge of -2, sodium has a charge of +1. So in order to balance the charges there, we need to have 2 sodium ions for every carbonate ion. And so that's where the subscript 2 comes from for the sodium and sodium carbonate. And then finally for sodium nitrate, nitrate is a -1 and sodium is a +1, so it's written just NaNO3. So it's very important that you look back to your polyatomic ions chart. Make sure that you know the charges on all of these ions so that you're writing the formulas correctly. And this just goes back to how we wrote those formulas to start with for ionic compounds. So that's coming back here. And then the next thing to check is to look for your 2 products and predict whether they are going to precipitate or not. So the silver nitrate contains a group 1A cation, so that means it is soluble, so it will stay in an aqueous solution. And notice that neither the cation nor the anion are on your solubility list, so we're going to predict that that will precipitate out of solution and form a solid. Okay, so the next thing is writing that ionic equation. So here we're taking all of the strong electrolytes and separating them out into their ions. So the silver nitrate separates out into silver ions and nitrate ions. And I should have mentioned before, when you're writing this formula, so here's the formula to start, the next thing you need to do is to balance the equation. So notice here that the balanced equation has a 2 in front of silver nitrate and a 2 in front of sodium nitrate. That's obviously very important. You need to make sure that that's a balanced equation before you move on. So then we get the numbers correctly here. So we've got 2 silver nitrate, so that's going to break up into 2 silver ions and 2 nitrate ions. We know that their charges are +1 and -1. We've got sodium carbonate. We know carbonate has a -2 charge, and we know that each sodium ion has a +1 charge, and there's 2 of them. So that's where you get the 2 in the front. And then the products here, we know that silver carbonate is a solid, so it stays intact as is. And the other product is sodium nitrate, and we split those into their ions, the sodium ion with a +1 charge and the nitrate with a -1, and there's 2 of each of those. So we have the ionic equation. The next step would be the net ionic equation. So what we're going to identify are those spectator ions that are appearing on the left and the right of the equation. And so they're shown here just sort of crossed out. And so your net ionic equation is what you see on the bottom. A little bit about some acids and bases that we'll talk about next to those types of reactions. So a definition according to Arrhenius of an acid is a substance that dissociates in water to produce hydrogen ions. So you can see 2, just a general example, and then one for hydrochloric acid here. And in water, acids produce, excuse me, hydronium ions, which is the H3O+. Base, according to the same definition, is one that dissociates in water to produce hydroxide ions. Excuse me. And you can see the general reaction here, and then one for sodium hydroxide. Another one to note that does not itself dissociate into hydroxide ions is ammonia. So while ammonia does not have an OH attached to it, it is also considered, also considered a base. You should know this table, so some common acids and bases. The ones at the top of the table are your strong acids and strong bases. The ones at the bottom are your weak acids and weak bases. And as we talked about previously, your strong acids and strong bases are going to be strong electrolytes. They're going to fully dissociate in water, and so that's why they will conduct electricity. The weak acids and weak bases are weak electrolytes. They will not dissolve very much in solution. These are some common oxoacids and their anions. I'll not hold you responsible for this table, but these are probably some you've seen before. Okay, when we talk about a binary acid, this is how we name them. So what you'll notice here is they all start with hydro, and then the second thing that it's combined with is the name with an IC ending and then the word acid. So hydrogen and chlorine together become hydrochloric acid. Hydrogen and bromine become hydrobromic acid. Hydrogen, fluorine, hydrofluoric acid. These types of reactions, the acid-base neutralization reactions, These are just double replacement reactions like you saw before. The main difference is you're getting a salt and water as products. So there's no looking for whether something's, the products are always going to be that salt and water. We'll look at a couple of examples. So here we have, write the molecular ionic and net ionic equations for the reactions of hydrobromic acid and aqueous barium hydroxide. So again, when you're looking at these equations and you're trying to figure out how to write the reaction, you need to first identify what type of reaction it is. So in this case, when you see HBr, you should know that that's an acid, and aqueous barium hydroxide, you should know that's a base. So I'm reacting an acid and a base, so I am identifying this as a neutralization reaction. It's very important that you're able to do that to start so that you know how to properly write the chemical equation. So we know it's an acid and base reaction, so we know one of our products is always water, and then whatever is left becomes the salt. So I'll talk through that. So we've got HBr and then BaOH2. The acid contributes the H to the water, and the base contributes the OH to the water. And then we just combine what's left. So if we remove the H from the acid, that leaves us with the bromine. If we remove the OH from the base, it leaves us with the barium. And so barium bromide becomes our salt. That's always the case when you're dealing with acid-base reactions. That's how you combine them and how you figure out what is the salt that I'm producing in this reaction. A little bit about the writing here. So hydroxide ion is a polyatomic ion. It has a charge of -1. Barium has a charge of +2, so that's why you need 2 of those hydroxide ions. HBr is just a 1 and 1. Then when you look at your salt, when you write barium bromide, you need to balance charges there. You know the bromine is a -1 because it's a halogen group, and barium is a +2 because it's a group 2. And so you need 2 of those bromine ions for every 1 barium, so that salt becomes BaBr2. Again, this goes back to being able to write equations for ionic compounds. So if you haven't practiced that, you want to make sure that you're really getting that practice and have that down. So the next thing here for the molecular equation is to balance the equation and then predict the solubility of the salt in the products. So barium bromide, if we use the solubility rules, we'll see is not on there. Is on there, so it is soluble in water, so it stays in aqueous solution. And the water that's produced here is just liquid water. And then balanced by putting numbers in front as needed. So the next would be the ionic equation. So now we're going to dissociate that strong acid and the soluble ionic compounds. So the HBr dissociates into H+ ions and Br- ions. The barium hydroxide into barium and hydroxide ions. And then the products, water is as written, it stays together. And the barium bromide salt that we have splits into the barium ions and bromine ions. Net ionic equation, you're just removing those ions that are on the left and the right side of the equation and writing what's left. And you'll notice that the net ionic equation here is the formation of water, and that is the ionic equation you should see for an acid-base neutralization reaction. Unless, let's see, so unless you end up producing a salt that is insoluble, in which case you would end up with that also included, I believe. Okay, so here's another example. Write molecular ionic and net ionic equations for the reaction of sodium hydroxide and aqueous hydrofluoric acid. So again, identifying that this is an acid-base reaction, we know we get a water and a salt. The salt that's produced here is sodium fluoride, the fluoride from the acid, the sodium from the base. I'm going to go through this rather quickly because we've done a few of these by now. So molecular equation, you want to balance it, use your solubility rules, and you'll find that sodium fluoride is soluble. Ionic equation, dissociate your strong acids and strong bases, so your sodium hydroxide here. Hydrofluoric acid stays aqueous because it's a weak acid. You produce water, and then your salt splits into the sodium and fluoride ions. And then net ionic equation, you want to remove your spectator ions, and you'll see what's left here. And again, there is sometimes other things listed in your acid-base reactions. If you have something other than a strong acid and a strong base that are reacting, you will get other combinations. So just make sure you're canceling what's on the left and the right and including what's left. Okay, the next types of reactions are known as reduction reactions or redox reactions, oxidation reduction reactions, and they involve transfer of electrons. So we'll talk a little bit about those types of reactions and how to identify them, and then how to write those reactions, write the products. So I'm going to skip this for a moment. First, the definitions of what we mean by that. So an oxidation reaction is one where there's a loss of one or more electrons. A reduction is when there's a gain of one or more electrons. This is a common misconception for students, that reduction is the gain of electrons. It comes from the fact that you're actually reducing by adding those electrons. You're essentially adding negative charge, so you're reducing the charge. That's where the name comes from. Anyway, definitely memorize these. Oxidation is loss of electrons. Reduction is gain of electrons. In order to identify these types of reactions, you need to be able to do this next sort of skill, which is to identify the oxidation number of any element. You can do this for anything. It doesn't have to be specifically a redox reaction. You can do it for any compound. And essentially, you have been doing this all along. You've been using what we're going to talk about as oxidation numbers to write formulas. It's when I've said, this has this charge, and so you have to balance it off with writing 2 of the other. That's what you've been doing here. So this should sound familiar to you. We're just using it in the terms of redox reactions, so we call these oxidation numbers. So here are our rules for assigning them, and then we'll do some examples. An atom in its elemental state has an oxidation number of 0. So neon here, sodium, and then recall those atoms that occur as diatomic atoms, a couple listed here, hydrogen and bromine. They all have oxidation numbers of 0 because they're in their elemental state. An atom in a monatomic ion has an oxidation number identical to its charge, and it should also say, and its charge is equal to its group number that you know by now. So the oxidation number for sodium is +1, calcium is +2, aluminum is +3, chlorine is -1, oxygen is -2. Again, this is coming from their location in the periodic table. So oxygen is in group 6. It would like to gain 2 electrons, so its charge, and now we're referring to these as oxidation numbers, is -2. Sodium is in group 1. It would like to lose an electron, and when it does, it takes a charge of +1. And so that's the oxidation number of sodium ion is +1. Atoms in polyatomic ions usually have the same oxidation number it would have if it were a monatomic ion. So for example, oxygen most likely will have an oxidation number of -2. There are a couple of things to note here. Hydrogen can be either +1 or -1. It depends on what it's in combination with, and I'll walk through the examples that are here. Oxygen usually has an oxidation number of -2, but if it needs to, it can take on a different oxidation number. So let's look at these examples. So the first is a polyatomic ion hydroxide. We know it has an overall charge of -1. So if we took oxygen to have a charge of -2, in order to get an overall charge of -1, that hydrogen has to have a charge of +1. So those are the oxidation numbers for hydrogen and oxygen in that compound. If we look at calcium hydride on the right here, we've got calcium and 2 hydrogen ions. Calcium we know has a charge of +2 from its group number. Because of that, in order to balance that out, each of those hydrogen ions must have charges of -1 to get to a net of 0. The oxygen examples on the bottom, so if we look at water, water has an oxidation number of -2 usually. And hydrogen, to balance that off, each hydrogen has a charge of +1. Your default for oxygen is -2 unless it doesn't work in the compound that you're given. And that's the case on the one on the right. So if you look here, you've got 2 oxygen atoms and 2 hydrogen atoms. Hydrogen can only be +1 or -1. Okay, it can't take on any other number besides +1 or -1. So when oxygen can be a -1, it's typically never a positive oxidation number. But if you take the oxygen to be an oxidation number of -1, then you can see how this might work. So if each oxygen atom has an oxidation number of -1, that's a -2, and then each of those hydrogen ions has oxidation numbers of +1, that's your +2, so it nets out to 0. In all of your cases, you need to make sure that your oxidation numbers sum to either a net of 0 if there's no charge on the compound, as is the case in all but one here, or that they sum to the overall charge, like in hydroxide with -1. And that depends on what you're given. Okay, if it doesn't have a charge to it, then those oxidation numbers must sum to 0. If you're given, say, a polyatomic ion, then the oxidation numbers must sum to the overall charge on that polyatomic ion. Another part here, halogens usually have an oxidation number of -1. So in hydrochloric acid, H is +1, chlorine is -1, no problem. If you look at the next example, oxygen is -2, so that means that each of those chlorines must be +1. So again, it's a matter of figuring out what will work and knowing that halogens can vary their oxidation numbers. It's usually -1, but if need be, they can take on a different oxidation number. This is what I mentioned before. The sum of the oxidation numbers is 0 for a neutral compound and has to be equal to the net charge for a polyatomic ion. Okay, a little bit more about defining redox reactions. What I usually tell students is to memorize one of these two charts because the other is just the opposite of one of these two halves. So it's up to you, or write it down on your sheet. A reducing agent is one that causes reduction, loses one or more electrons, undergoes oxidation, and the oxidation of the atom increases. One of the things to be able to do from these reactions is to identify any of these quantities. So to identify the reducing agent or oxidizing agent, to identify what's causing reduction, what's causing oxidation, to identify what loses, what gains electrons, identify what undergoes oxidation, what undergoes reduction, and identify what oxidation number increases and decreases. Okay, so you'll need to be able to identify all of these things that we'll go through. So an oxidizing agent is sort of the flip side. This causes oxidation. It gains one or more electrons. It undergoes reduction, and the oxidation of the number of the atom decreases. So here's an example. So we've got iron and oxygen forming iron oxide. One thing to note is that when you're looking at redox reactions, you're always looking at the left-hand side and the reactants to identify what's the reducing agent and what's the oxidizing agent. You never, ever look at the products or say a product is a reducing agent or an oxidizing agent. That's incorrect. So it's one of the two reactants is being reduced, one of the two reactants is being oxidized. You have to identify which is which. So the way to do that is to see what the oxidation numbers are. That's why you had to learn that skill from before. So iron in its solid state has an oxidation number of 0 because it's in its elemental state. Oxygen as a gas, O2, has an oxidation number of 0 as well. Now look at the right-hand side. In the product they're forming, oxygen has an oxidation number of -2 from its group number. There's 3 of them, so that's a total charge of -6. And iron has a charge of +3. 2 of those balances that off, +6. So notice what's going on here. The iron in the reactant is an oxidation number of 0. The iron in the product has an oxidation number of +3. So has iron gained or lost electrons? Electrons are negatively charged. It has lost electrons. How many? 3. So iron on the left-hand side loses 3 electrons to form that iron oxide. Let's look at the oxygen. Oxygen goes from an oxidation state of 0 to -2. Did oxygen gain or lose electrons? It gained electrons, specifically 2 electrons, to change to that oxidation state. So if you were asked other information here, you would say that iron undergoes oxidation because it has lost electrons. Oxygen is undergoing reduction because it's gaining electrons. You could also say that iron is the reducing agent and oxygen is the oxidizing agent. Okay, so all of those things fold in together. And it relies on identifying those oxidation numbers and then being able to use those to see what's going on, what's the change that's occurring. And remembering that electrons are negatively charged. So if you're seeing an increase towards the positive charge, that means that you're losing electrons. So 0 to +3 means you've lost 3 electrons. If you're going more negative in charge, that means you're gaining electrons in the number that you have changed. Here's another example. So iron oxide, to start here, the oxygen is -2. There's 3 of them, so total charge on oxygen is -6. Iron's +3, there's 2 of them, +6. So oxidation number on iron is +3 to start. And the product is iron in its solid state, which is its elemental state. Okay. I'm thinking for a minute. Don't know why that's -2. I'll come back to that. And then if you look at your carbon, carbon is in its solid natural state, and so its oxidation number is 0. If you look at carbon in the carbon dioxide gas that's formed, so if we look at that, that CO2, oxygen's oxidation number is -2. There's 2 of them in that compound, so the total charge on oxygen is -4. So the charge on carbon in that compound is +4. So if we look at carbon, we can see it went from an oxidation state of 0 to +4. So did it gain or lose electrons? Lost electrons, lost specifically 4 electrons. Iron goes from a state of +3 to -2. Did it gain or lose electrons? It gained electrons. It gained 5 electrons. And since the carbon is the one that has lost electrons, it's also referred to as the reducing agent. It undergoes oxidation. Likewise, the iron is reduced, and the iron oxide is the oxidizing agent. Okay, this is a sort of separate topic here. This is being able to predict whether reactions will occur. Let me get to the right chapter, the right section. So if we take these 2 reactions that you see here, there's a table on page 255 in your text, and unfortunately it's not the table that's listed here. So this table 7.4 is improperly placed in this lecture slide. So I'll have you refer to page 255. That lists the partial activity series of the elements while I talk through this. And you would be given this, so you do not need to write this on your exam sheet. You'll be given the activity series. And you'll notice that at the top is sort of says strongly reducing, and at the bottom says weakly reducing, and it's listed in order in which they will occur. Okay, so in this type of problem, you're usually given 2 problems and asked which of these reactions will occur. And there's sort of a cutoff that says these elements do not react with aqueous H+ ions to release H2, in which case you'd say the reactions wouldn't occur. And the ones above it occur, and then if you were asked which one would occur more favorably, you look to see which one is higher up in the chart. So anyway, so the example that's given here, copper to copper 2+, and then silver to silver plus. And if you look at the ions there, the one on the top is sort of right below where the hydrogen is, and the silver is even further below that. So these will not react with aqueous ions to release hydrogen gas. They're in that last sort of category. So that's really the answer to that question. The ones that are above where the hydrogen are, you could determine which would occur faster. So I'll give an example that you can see on that chart if you have that in front of you. If you had, say, magnesium to magnesium 2+ ions, and then calcium to calcium +2 ions, you can see that the calcium is further up on the chart. So that means that that reaction would happen faster, more rapidly, than the reaction that produces the magnesium 2+ ions. So that's basically how you use that activity series. Again, the higher up on the chart, the more rapid the reaction will occur. Okay. We are actually going to skip this. Breathe a big sigh of relief because it's fairly involved. And this is section 7.9, balancing redox reactions by the half reaction method. You can feel free to look through that. I'm happy to answer questions on it, but I will not put this on the exam. So we'll skip right through these. And there's a few of them. Okay. This just talks a little bit about titration, which I know you're doing in the lab, so I'm not going to really go through this. But I will show you this type of problem really is what we've already talked about in the previous chapter. And this is just using stoichiometry to address a question. So you're given 0.2585 grams of oxalic acid. That's the first reactant there. And then 22.35 milliliters of an unknown solution of potassium permanganate. So you're trying to find the overall molarity of potassium permanganate in the answer. So you're given a mass. You know, when you're given a mass, to convert that to moles without even thinking too much. So that's sort of the first step. Figure out the moles of oxalic acid you have, and then figure out what are the moles of potassium permanganate you would need to react with it, and that you would use the mole ratio. So you can see in this equation there's 5 moles of oxalic acid to your 2 moles of the MnO4 is the ion that's used here in the potassium permanganate. So to 2. Figure out the moles of KMnO4 that you need, and then or that you would have. And then they've given you a volume, so 22.35 milliliters. Use that to calculate the overall molarity of that KMnO4. Again, this is really just a different kind of application, but on stoichiometry that we have already talked about. And so this sort of talks through that, but I'll leave that to you to look at if you'd like. These are just some applications of redox reactions. And we'll end there.